Good morning, my students. Today we are learning about double titration. This is the next example. We have seen the first one. So this question is asking, you are provided with solution N, hydrochloric acid, solution M, sodium hydroxide, solution Y, diabasic acid, H2A containing 2.3 gram of 250 centimeter cubic of solution. We have procedure 1. Procedure 1, fill the burette with diabasic acid, then you pipette 25 centimeter cubic of sodium hydroxide solution, then you place in a clean conical flask. So this is the final reading: 28.0, 28.0, 28.0, initial 0.0, 0.0, 0.0, final reading of volume of H2. Volume of H2 of diabasic acid is 28, 28.0, 28.0, 28.0. So let us see the questions. The first question, obviously, calculate the average volume. Calculate the average volume of the diabasic acid. So to calculate the average volume, you pick these values. These values here, 28, 28, 28, 28. So you add all of them, 28.28 plus 28 plus 28 divided by 3. All of them, when you add the 3, you will get 84 divided by 3, then you will get 28.0 centimeter cube of diabasic acid you used. This is the volume of the diabasic acid used out of 250. Now question 2, that was question 1. Question 2, the concentration of the diabasic acid in gram per liter. To calculate the concentration of diabasic acid in gram per liter, we have the mass, which is 2.3, and the total volume, which is 250. Then this is what you do. 2.3 gram is equal to 250. What about 1000? 1000 represents concentration. Cross multiplication. You multiply this one and this one, then 250 it will go down. When you multiply 2.3 times 1000 divided by 250, you will get 9.2 gram per liter. Question Roman 3. Roman 3 is asking the concentration of the diabasic acid in moles per liter. Question 3, that was Roman 2. Roman 2, we have understood concentration of the diabasic acid. You equate the mass, the total volume. What about 1000? You cross multiply, where you get 9.2 gram per liter. Question Roman 3, the concentration of the diabasic acid in moles per liter. Given that H2C2O4, which is the diabasic acid, where C is equal to 12, H is equal to 1, oxygen is equal to 16. Then first, concentration in moles per liter means molarity. Molarity is equal to concentration gram per liter over RFM. So you have to calculate the RFM. Concentration gram per liter, we have it here, it's here. We have it here. So we need to calculate the RFM of H2C2O4. So H is always 1 in the bracket here. Then we have 2 hydrogen. 1 times 2 plus 2. We have 2 carbon here, and each carbon is 12 here. Then 2 carbon times 12 plus 16, which is oxygen is 16, and we have 4 oxygen here. Okay, 16 times 4. Then here you will get 2. 1 times 2 is 2. Then 2 times 12 is 2 times 12 is 24. 16 times 4 is 64. When you add 2, 24, 16, you'll get 90. Then molarity therefore is equal to 9.3. I mean 9.2, which is the concentration in gram per liter in Roman 2. 9.2 divided by the RFM, which is 90. Then you get 0.1 molar of diabasic acid. Very good. Very good. Very good. Now, the next question is asking Roman 5. The number of moles of the diabasic acid. The number of moles of the diabasic acid. To calculate the number of moles of the diabasic acid, you have the molarity of the diabasic acid. You have also the average volume. This is the average volume of the diabasic acid. And you have the molarity. Then this is what you do. Molarity is equal to 0.1. Molar is equal to 1000. Then what about 28 centimeter cube of the average volume used? You cross multiply 28 times 0.1, then divide by 1000. Then when you do that, you'll get 0.0028 moles of the diabasic acid you used. That's how you do in Roman 4. Roman 4. I think you have understood Roman 4. We go to Roman 5. Roman 5 is asking the number of moles of the sodium hydroxide solution used. To calculate the number of moles of sodium hydroxide used, you already have the number of moles of the dibasic acid used. Then therefore you use an equation, then you balance it. Roman 5, Roman 5. Roman 5, you react sodium hydroxide plus H2A, the dibasic acid H2A. We don't know A. The N is the anion. We don't know that the anion of that acid H2A. Then you get sodium A plus water. Sodium A plus water. Where here sodium takes 2 because the acid is dibasic. It contributes a radical of valence 2. A is a radical and it has valence 2. Then when you balance the equation here, sodium here 2, then you put it here 2, sodium 2. Okay, oxygen here 2 because this 2 is multiplied across. Oxygen 2, here oxygen 2, here oxygen, oxygen 1 here, oxygen 1 here. Oxygen is only 1. So to balance oxygen, you put 2 here. 2 oxygen, yes, balance. Then you come to hydrogen. Hydrogen 2 here plus 2, 4 hydrogen here. Hydrogen 2 times 2, 4 balance. Okay, so the mole ratio becomes now in the reactant side 2 to 1. So 2 is sodium hydroxide, 1 is the dibasic acid. So here you have the number of moles of the dibasic acid as 0.0028 and its mole ratio is 1. Then you'll say 1 mole ratio is equal to 0.0002028. Then what about 2 mole ratio of the sodium hydroxide? How many moles will it be equal to? We don't know. We cross multiply. 2 times 0.0028 divided by 1. Then this is what you get, 0.00056 of moles of sodium hydroxide. This is the number of moles of sodium hydroxide used. So that's how you calculate Roman 5, the number of moles of sodium hydroxide used. You use equation and you balance. Roman 6, the concentration of the sodium hydroxide solution. To calculate the concentration of sodium hydroxide solution, you need the volume used. This is the number of moles of sodium hydroxide used. This is the number of moles of sodium hydroxide. This is the number of moles of sodium hydroxide used. So if this is the number of moles of sodium hydroxide used, do we have the volume used? Let us look it. The volume used is provided in the equation. So here we have next. Here we have 25 centimeter cubic of sodium hydroxide solution. Using a pipette, place 25 centimeter cubic of sodium hydroxide solution. This is the volume used of sodium hydroxide. So therefore 0.056 moles, which is the moles used, is equal to the volume used, which is 25 centimeter cubic of the volume used is equal to 0.056 moles of the volume of the number of moles used, because they are equal. What about 1000? Concentration in terms of concentration moles per liter, which means the molarity in terms of volume is equal to 1000. Then you cross multiply. You multiply 1000, 0.0056 divided by 25. This is what you will get. This is the molarity of the sodium hydroxide. Yes, the sodium hydroxide molarity still remains the same. Why? Because the volume is equal. The two volumes of the two procedure 1 is equal. The volume is 0.224 moles of sodium hydroxide is used. Okay, let us go to procedure 2. Procedure 2, now we are reacting the sodium hydroxide. This time we are reacting the sodium hydroxide with the acid. We will react sodium hydroxide with hydrochloric acid. Then using 100 ml measuring cylinder, measure 10 centimeter cubic of hydrochloric acid. This is the original volume of the hydrochloric acid, 10 centimeter cubic. Then you add still water up to the mark. Then you label a solution R, not F. Here is solution R. Solution M. You label it solution M. So then fill the burette with solution M, the new solution that you have prepared, that you have diluted. Then using a pipette, you place 25 centimeter cubic of sodium hydroxide solution in a clean conical flask. Then you add 2 drops of methyl orange, or phenolphthalein indicator. Then you carry out the titration. You fill the table. Now the table here, final reading of the burette is 25, 25, 25, 25. So initial 0.0, 0.0, 0.0. Here 25.0, 25.0, 25.0 volume of HCl used. You subtract. So the first question, obviously, calculate the average volume of hydrochloric acid used. Average volume, you add the 3, this 3, 25, 25, 25, then you divide by 3, 25, 25, 25, 25, divided by 3, you'll get 75. When you add them, you divide by 3, you get 25 centimeter cubic of HCl used. Question 2 is asking the concentration of the hydrochloric acid in moles per liter in 100 centimeter cubic. To calculate the molarity or the concentration in moles per liter of the hydrochloric acid, you start from the side of the base. You'll start from the side of the base because in hydrochloric acid you don't have anything. First you get the number of moles of the base. So to get the number of moles of the base, 0.022 moles of the, which is the concentration of the base that we have here, that we have obtained here. Sorry. 0. What was the concentration of the base? Okay, this is where we were, is it so? Okay, this is the where we were. So the concentration of the base was 0.224 moles of sodium hydroxide. So this was the molarity. Then you'll say that molarity, which is 0.224 moles, is equal to 1000. What about 25? This 25 is the volume of sodium hydroxide used, which is this one. Then you cross multiply, you'll get 0.224 moles of sodium hydroxide times 25 divided by 1000. Here you will get 0.0056 moles of sodium hydroxide. Still you don't have the number of moles of the acid. And the reason as to why we are looking at the number of moles of the acid is we want to use that number of moles of the acid to lead us into the molarity of the acid. Okay, when you get the number of moles of the base, then next step, you write an equation, which is sodium hydroxide plus hydrochloric acid, then sodium chloride plus water. You balance the equation, then the mole ratio, you check the mole ratio. The mole ratio is 1 to 1. Since the mole ratio is 1 to 1, the number of moles of the acid is 0.0056 moles. It remains the same. It remains the same. Then now we have the number of moles of the acid. Since you have the number of moles of the acid, this is the number of moles of the hydrochloric acid used. And what is the volume of hydrochloric acid used is the average volume. This average volume 25. They are equal. This one is equal to that one. Then what about 1000? 0.0056 moles of the hydrochloric acid is equal to 25, which is the average volume. What about 1000? Then you cross multiply, you will get 0.224 moles of sulfuric acid. Hydrochloric acid. The molarity of the acid and the molarity of the base are equal because the two volumes are equal. Both volume are equal. Both volume, average volume is 25, and the pipette volume is 25. That's why the two molarities are equal. Then when you have that, that's how you solve question 2. Question 2 was very long because to calculate the molarity of the acid, you need a longer procedure to follow. First you get the number of moles of the acid. To get the number of moles of the acid, you have to get the number of moles of the base. In the base, you have molarity. Molarity is equal to 1000. 25 of the volume of the base is equal to how much? Cross multiplication, which is the pipette volume. When you get the number of moles of the base, then you write the equation, you balance it, then through mole ratio, you get the number of moles of the acid. Since the mole ratio is 1:1, the number of moles of the acid remains the same with that of the base. Then that number of moles of the acid is equal to the average volume, because the average volume is the volume used, and this is the number of moles used. They are equal. Then what about 1000? That's how you'll get the molarity of the acid. Then we have another question. The last question, which is Roman 3, is asking the concentration, the original concentration of the hydrochloric acid in 10 centimeter cubic. To calculate the original concentration, you use this formula. Molarity 1, volume 1 is equal to molarity 2, volume 2. Molarity 1, we don't know. That's what we are looking. Volume 1 is 10, because the original volume of the acid when we were pipetting was 10 centimeter cubic. Then 10. Molarity 2 we have obtained right now, 0.0224. This is the molarity 2. Then original volume is 100. Volume 2 is 100. It's here. We have diluted up to 100 ml. We have diluted up to 100 the solution. Okay. Then you substitute the formula. Then this is what you do. M1 that you don't know times molarity 1, volume 1, which is 10, is equal to molarity 2, M2, which